So, what if I told you that you could use heat to make something cold? Or, get this, use some lukewarm waste heat from a factory to generate really hot water for a building. I know, it sounds like it completely breaks the laws of physics, right? But it's the reality behind this really fascinating technology called thermally driven heat pumps. So let's dive in and see how they basically turn our whole understanding of heat completely on its head.
So here's what we're going to cover. First, we'll look at the massive, kind of hidden energy problem that these things are trying to solve. Then we'll get into the weird core concept of using heat to actually move heat. After that, we'll peek inside the machine, see how it actually performs out in the real world, and finally, we'll talk about what the future looks like for this technology.
Okay, so first things first, let's set the stage. You know, the simple act of staying warm in the winter and cool in the summer, well, that's one of the single biggest energy hogs on the entire planet. And that demand, it's growing fast. It's this massive and honestly, mostly invisible strain on all of our energy systems.
I mean, just think about it for a second. Everything from giant office buildings and industrial plants all the way down to our own homes needs some kind of temperature control. And right now, we mostly do that by either burning fossil fuels or by using a ton of electricity. That just puts a crazy load on the grid, especially, on those super hot summer days. The way we're doing it now just isn't sustainable. And that's exactly why we need a totally different way of thinking about heating and cooling.
And this is where we get to the core idea behind thermally driven heat pumps, or TDHPs. And it's such a cool, counterintuitive concept. What if, instead of using super valuable electricity to do the work, what if you could use a source of heat itself to power the whole heating or cooling cycle?
So what exactly is a TDHP? Well, at its heart, it's a machine that literally uses heat as its fuel. And this can be anything. Waste heat from a data center, solar thermal panels, or even the heat from burning natural gas. It takes that energy and uses it to power a process that actively pumps heat from a cold place to a warmer one.
Okay, so let's put this side by side with a regular heat pump, the kind you might already have. On the left, a conventional one. It uses high-value electricity from the grid to run a big mechanical compressor. But a TDHP, on the right, uses a source of heat, like, say, waste heat from a factory, to run a thermochemical process instead. And here's the crucial difference, the impact. One adds more strain to the electrical grid, while the other can literally run on energy that we would otherwise just be throwing away.
To make this make sense, let's use an analogy. Imagine you have a special liquid that acts like a sponge for a refrigerant gas. At low pressure, it just soaks that gas right up, no problem. Then you add your driving heat. This is like squeezing the sponge, hard. It forces the refrigerant out as a high-pressure vapor. And it's that pressure, that squeeze, that powers the entire cycle, all without a single mechanical compressor.
All right, so let's see how that sponge idea turns into a continuous loop. It's basically 4 steps. First up, generation. This is where your driving heat boils the refrigerant out of that sponge solution. Second, condensation. That hot, high-pressure vapor moves over to a condenser, where it cools down, releases its heat, and turns back into a liquid. Third, and this is where the magic happens, evaporation. The liquid refrigerant flows into the evaporator, and as it turns back into a gas, it sucks up a ton of heat from its surroundings. That's your cooling effect. And finally, absorption. The vapor gets reabsorbed back into the sponge solution, and the whole cycle is ready to go again.
Okay, so that's the principle. But what do these things actually look like? What are they made of? Let's go from the concept to the actual physical hardware.
The real engine of a TDHP is what's called its working pair. That's the refrigerant and the absorbent, the sponge. The two most common pairs have some pretty clear trade-offs. On one hand, you have water and lithium bromide. It's super efficient, totally non-toxic, but you have to be careful it doesn't freeze or crystallize, so it's great for things like air conditioning. On the other hand, you've got ammonia and water. This combo can get incredibly cold. We're talking minus 40 Celsius. But ammonia is toxic and you need high-pressure gear, which makes it a better fit for heavy-duty industrial refrigeration.
And that chemical sponge isn't the only way to do it. Check out this other really clever design. Instead of a chemical process, this one uses the driving heat to run a tiny little heat engine. Think of it like a miniature power plant. That engine spins a turbine, which then drives a compressor, just like in a regular heat pump. So you see, heat is still the fuel for the whole system. There's just a mechanical link in the middle.
And here we go, from the drawing board to the real world. This is an actual experimental absorption chiller at a university in Berlin. They use it to test brand new working fluids, trying to push the boundaries of what this tech can do. This just makes it so tangible, you know? These aren't just theories on a page. These are real machines being built and tested today.
Okay, so the theory is solid, the prototypes are real, but how do these things actually perform when you get them out of the lab and into the real world? Let's look at the numbers. The key number for any heat pump is its coefficient of performance, or COP for short. A typical TDHP might have a COP of 1.5, so what does that even mean? It means for every 1 unit of heat energy you put in to drive it, the machine delivers a total of 1.5 units of useful heating. It's literally grabbing that extra half unit of energy from the surrounding environment. You're basically getting energy for free.
And this isn't just theory. Check out this chart from a real field trial. They took a gas-fired heat pump and put it up against a brand new, top-of-the-line gas boiler. The result? The heat pump was 35% more efficient. That's a huge deal. It means you're getting way more heat for the exact same amount of fuel because it's pulling in that extra free energy from the air.
Now, to really see the potential here, we have to look at this fantastic case study. And it's not a house or an office building, it's a composting plant in Germany. So at this plant, the whole composting process creates a ton of hot, humid air, and they have to cool that air down before they can filter it. Now, instead of just wasting all that heat, they use it to power a massive TDHP. So the machine does two things at once. It cools the air, solving their problem, and it uses that captured energy to make hot water for the local town's heating system. It's just brilliant. It turns an environmental problem into an energy solution. But, real-world projects always have real-world problems. At that plant, it turned out a simple communication error between the heat pump controller and its backup gas burner was causing issues. The system couldn't adjust its power correctly, so it kept switching on and off, which really hurt its efficiency. It's just a great reminder that the fanciest hardware in the world doesn't mean much if the integration and the controls aren't dialed in perfectly.
So all of this brings us to the future. TDHPs are a proven, really powerful technology, but there are still some barriers to overcome. And, of course, some really exciting breakthroughs on the horizon.
So on the challenge side, you've still got tough engineering problems like corrosion from high temperatures and the ongoing hunt for even better, safer working fluids. But the opportunities? They are huge. Researchers are working on things like membrane absorbers that can make these units way smaller. And honestly, the single biggest opportunity is just system integration. Getting really clever about matching these machines with all the waste heat that our world has already produced.
And really, that's the thought I want to leave you with. We are literally surrounded by sources of low-grade heat. From industrial plants, from data centers, even just from the sun hitting the roof. This technology gives us a real way to actually harness all of that. So the question is, as we look for new energy solutions, could it be that our biggest untapped resource is the very heat that we're currently just throwing away?